Okay, this section is about enthalpy changes for chemical reactions. And the goal is to understand and use enthalpy change for conversion of reactants to products in their standard states. So what does a standard state mean? Basically means 25 degrees Celsius and 1 atmosphere of pressure. There are many aspects of delta H that are important. Remember, H is enthalpy, so this is the standard enthalpy change. Okay, so here's two important things: that if delta H is negative, it's an exothermic process or reaction. And if delta H is positive, it's an endothermic process or reaction. And we're going to focus on this part here for this particular section for the moles of reaction as written. So here we have 1 mole of H2 reacts with 1/2 mole of O2 to give you 1 mole of H2O gas. And the change in enthalpy is negative 241.8 kilojoules. That means 241.8 kilojoules is released, or it's a product. So here we could write for the reaction, if we want to focus just on the oxygen being used, that we get 241.8 kilojoules per every 1/2 mole of oxygen that reacts. Or we can focus on the H2O, and it's minus 241.8 kilojoules per 1 mole of H2O. These things are not additive. This is saying, well, if we focus on this one particular substance in the reaction. Also, if you take this reaction and reverse it, so if we make the H2O a reactant instead of a product, like I've done here, and take the H2 and O2 and make them products instead of reactants as they are here, you also change the sign on the enthalpy. So this becomes positive 241. So to take H2O gas and to turn it into H2 gas and O2 gas, you have to put 241.8 kilojoules of energy into it. Some other aspects is that delta H depends on the state. So in this top reaction, you'll see that we're making H2O gas, and 241.8 kilojoules is released in this reaction, an exothermic reaction. However, if we make H2O liquid from the same reactants, 285.8 kilojoules is released. So the delta H amount depends on the states of the materials in the reaction. Also, delta H can be written in the reaction. So if we look at this reaction right here, which is an exothermic reaction because delta H is negative, so an exothermic reaction, we can write this energy as a product. And because it is a product, it's now a thing, and you don't say minus a thing, it's plus this product. So you get H2O plus this energy. So remember, the sign convention on energy has nothing to do with whether it's positive or negative energy, has everything to do with whether the energy is being absorbed or released. Released energy is negative. Released energy is a product. Released energy can be written as a product, but as a product, we put plus this product. Okay, so here in this reaction, we use a plus, not a negative. We only use the negative when we pull this out of the reaction. When we pull it out of the reaction, we say, hey, how do we know it's a product? Well, because it has a negative sign. For an endothermic reaction, it's the exact opposite. So if we wanted to split water apart, or I should say steam apart, and make it into H2 gas and O2 gas, we'd have to add 241.8 kilojoules of energy. So here, the energy is a reactant. Let's take a look at some problems doing work with this stuff. Okay, so here we have that sucrose can be oxidized to CO2 and H2O, and the enthalpy change for the reaction can be measured. So here we have 1 mole of glucose reacting with 12 mole of oxygen, give you 12 mole of CO2 and 11 mole of H2O. And for this reaction, this is the enthalpy change. Notice it's negative, and it's 56.45 kilojoules per mole for the reaction. So the reason they say mole for the reaction, because it depends on what you're looking at in the reaction for what you're actually going to use. So what is the enthalpy change when 5 grams of sugar is burned under conditions of constant pressure? So I want to take this 5 grams of sugar, and you'll notice this enthalpy change is given in per moles. So I want to turn that into moles of sugar. And then I can use this value to turn that into kilojoules. So how do we get the molar mass of sugar? Because that's what we need to go between grams and moles. Well, we have to do a little multiplying. So 12 times 12.01 grams is 144.12 grams. Then we have 22 times 1.01 grams, which is 22.22 grams. Then we have 11 times 16.00 grams. Now I know 10 times 16 is 160, so 11 times 16 is 176. Now when I add these together, I get 4, 3, 2, carry the 1, 4, carry the 1. I get 342.34. And this is only good to here because of the 4 zig fig, so this is only good to here. So we get 342.3 grams. So I'm going to take my 5 grams of sugar, multiply by 1 mole of sugar per 342.3 grams of sugar, and then times negative 5645 kilojoules per mole. Now here, it's going to be per 1 mole of sugar. Now, if they had asked about how many grams of O2, I would have used per 12 grams of O2, okay? Or 12 moles of O2, I'm sorry. So here, if we take a look at this value, you can see that this is going to go into this about what, 1, 2, 3, 15, 16, 17 times. 17 times 5 is, I don't know, 85. So the answer is going to be 8085. And it's going to have a negative value. Okay, so let's check it out and see what we get. 5 times 5645 divided by 342.3, and we get 82.5 kilojoules. And the negative is important because when we talk about the enthalpy change, this says that this releases 82.5 kilojoules of energy. And what is that energy used for when you eat it? Well, it's used to run your body. Okay, so this is how you do this calculation. Now, let's try another one. So here's another one for enthalpy changes. Nitrogen monoxide, a gas recently found to be involved in a wide range of biological processes, reacts with oxygen to give brown NO2 gas. So here it is, reacting with oxygen to give you brown NO2 gas. And the change in enthalpy of the reaction is minus 114.1 kilojoules, and this is per mole of the reaction. Is this reaction endothermic or exothermic? Well, we would answer first of all that since delta H is equal to a negative 114.1 kilojoules, negative being the important part here, it is exothermic. Okay, what is the enthalpy change if 1.25 grams of NO is converted completely to NO2? Okay, so we're going to start with 1.25 grams of NO, turn that into moles of NO, and then turn that into joules. So here's how we do it. 1.25 grams of NO times 1 mole of NO. And for NO, N is 14.01 grams. O is 16.00 grams. You add those together and you get 30.01 grams. Now, since the value is negative 114, we're at minus 114.1 kilojoules. And since we're talking about this in reference to nitrogen monoxide, we have to say per 2 mole of nitrogen monoxide. So why is this a 2 when it wasn't for sugar? And the answer is because this is the energy value for the reaction as written, and this is for 2 moles of NO reacting. Okay, so let's finish this off. We get 1.25. I'm going to estimate real quick. This 30 will go into a minus 114 about 4 times. 4 divided by 2 is 2. 2 times 1.25 is, I don't know, 2.5. Okay, so 1.25 times 114.1 divided by 30.01 and divided by 2, and we get 2.376. So the 7 becomes an 8, and this is negative kilojoules. Okay, so that's how much energy for 1.25 grams of NO. The negative signifies that this is energy released. Okay, good. Let's try one more, and then we'll call it quits for this section. So here's another enthalpy change. Isooctane, one of many hydrocarbons that make up gasoline, burns in air to give water and carbon dioxide. This is the molecular formula for isooctane, C8H18. Reacts with 25 oxygens, you get 16 CO2 and 18 H2O. And the change in enthalpy is minus 10,922 kilojoules for the reaction as written. Okay, what is the enthalpy change if you burn 1 liter of isooctane? So I'm going to take that 1 liter of, I'm going to call it isooctane. And actually, I'm going to cross that off, and I'm going to say I'm going to take my 1 liter of C8H18. I'm going to convert that into milliliters of C8H18. Then I'm going to convert that into grams of C8H18. Then I'm going to convert that into moles of C8H18, which I will then convert into kilojoules. Okay. So here we go. 1.00 liter C8H18 times 1,000 milliliters of C8H18 to 1 liter of C8H18 times, let's see, to go from milliliters to grams, we need the density. So 0.69 grams of C8H18 per 1 milliliter of C8H18. And then we need to use the molar mass of C8H18. So that's going to be 8 times 12.01 grams plus 18 times 1.01 grams. So the bottom one is 18.18 grams. The top one is going to be, let's see, 80 plus 96.08 grams. And we total that, and we get 6, 2, and 4. Carry the 1, and we get 11. So times 1 mole of C8H18 per 114.26 grams of C8H18. And then here from the balanced reaction, it's 2 mole of C8H18 to negative 10,922 kilojoules. Okay, so this looks like it's going to be a pretty big number because 114 goes into 1,000 10 times. 2 goes into 10 5 times. 5 times 0.69 is 3. And 3 times this is going to be negative 31,000 or 32,000, something like that. So let's check it out. 1,000 times 0.69 times 10, 922 divided by 114.26 and divided by 2 is equal to 32978. So I said around 31,000. It's pretty close. Now, for significant figures, basically that's going to limit us, 2 zig figs. So this becomes 33,000 kilojoules. And there's your answer. All right. Thank you for listening.